Hello friends, welcome to Abaqus Acumen for quick and sound learning. In today's video session, we are going to discuss about Abaqus linear buckling analysis. So let's get started. So what you'll get to know from this video. This video we are split it in three parts. The first part is talking about fundamentals of a buckling failure. Second parts talk about finite element buckling fundamentals, and the last part is actually hands-on training on a Abaqus example and the interpretation of buckling results. So typically if you see a practical sense and the feel for this buckling failure, we can do this small examples at home. You can take a steel rule, you put this steel rule on a table, give some firm support at the bottom, and through hand you try to apply a compressive loading. So as you start applying some compressive loading on a steel rule, at one particular situation with little increment in a load, steel rule get a buckle. So you see a suddenly high deformation at one particular load, and that particular load is called as a buckling load or a critical buckling load or a bifurcation point in a buckling term. Now other example to really get a practical sense and feel is you can take a 2 Coke can, and for example 65 kg man standing on this 2 Coke can, and then you slowly start shifting your weight on a 1 Coke can, and then you'll find a situation where with little increment in load a Coke can get buckles. Now beauty about this analysis is for either a steel rule get buckle or a Coke can get buckle, in both case there is no material failure. It is only at a little at one particular load you just add little bit load to that and the structure gets buckle. You see a high deformation. So that is actually most of the people refer as a buckling. Now let's get understanding more from the technical terms. What is a buckling? And then if you studied in your grad or undergrad engineering course, whenever somebody talks about buckling, you see a column structured and a compressive loading. And buckling is really a very unique and curious subject because it is the only structural mechanic problem in which failure is not related to a strength of material. And most of the time in this buckling analysis we are determining a maximum load where this structure get a collapse, and this collapse has nothing to do with the material yield. So there is no material yield. Mainly whenever this buckling is happen, it is mainly governed by two important parameters are like a material stiffness parameter and also a geometrical parameter, and this buckling failure is mainly due to a elastic instability. Now let's try to understand from the real time buckling failure. So where you see a buckling failure, now most of the people think buckling failure is very related to a column structure in a building construction industry, but the buckling is everywhere. You see in automotive or process industry, or you see building and construction industry. For example, now if you see picture on my left top corner, whenever a car go through a rollover case and where a pillar is get buckled because of a rollover case, or you see in a frontal crash scenario, the crash cans are used to get a control buckling in that case. Or something like if you see a very high pressure vessel, they are getting buckled due to a self weight. Or you see a pressure vessel related to vacuum pressure vessels, they get because of this high vacuum pressure, you see some buckling at the bottom. Similarly, you see in a building and construction industry, this column supporting a building dead weight, they get buckled. Also another example you see at the bottom right corner is a huge pressure vessel is get buckled due to its self weight. So these are some of the real time buckling failure. Now whenever we talk about buckling goes back in 1757 when Euler derived this classical formula called as the Eulerian buckling formula, and this buckling formula is started as a technical basis for a column buckling. Let's understand what this formula is, Euler buckling. So your maximum critical buckling load is actually a pi square EI by K into L square. So your critical load is directly proportional to your modulus of elasticity. Critical buckling load is also directly proportional to the area moment of inertia, and it is the inversely proportional to length square. Now this length is actually column length, and the effective length for this column is changing based on the end condition. So for example, if you have see the case number 2, where both end are a pin condition, so the effective length will be 1. But if you have one fixed and other free condition, then this effective length become 2L. You always get this effective buckling length factors when you go through this Eulerian column buckling formula. You can get all these formula details in textbook or open literature available. Now really try to understand this importance of buckling in today's world. Why actually buckling is so important in today's world? If you see today's world, which is mainly governed by material science, and in material science you see a lot of people talking about a high tensile strength material, whether it is steel, people talks about a composite material, glass fiber composite, carbon fiber composite. So for example, you see now in a windmill industry, which is mainly the length of the windmill are going from 60 meter to like 80 meter or 100 meter, and when they go for this long blade, the weight is a major criteria for them, and in that case they go for this high tensile strength composite materials, and for that they go for a thinning of a section, whether it is in spur cap or different sections of a windmill blade. And when they go for a thinning of the section, then you see the structure get buckles. So for example, windmill get buckles, or similarly you see the supporting tower for windmill, if you go for a very thin section, it get buckles. Now is a buckling all the time is a problem? Some people has taken buckling into their advantage. So for example, if you looked into a automotive industry at the bottom, in 1950, Mercedes-Benz used this buckling in their favor. So Mercedes-Benz design a passive safety design in which we have this crumple zone, then we have rigid passenger cell, and then you have crumple zone. So once you have in a frontal impact, the all energy, whatever kinetic energy coming from the impact towards the occupant is mainly get absorbed due to a control buckling. And once you do a control buckling in crumple zone, the passenger, the occupant is safe in a rigid cell, and that's what the Mercedes-Benz use this crumpling zone concept from a control buckling. And you can see the crumpling zone is still used as a passive safety measure in today's car. So you can use buckling also in your favor wherever you want to really protect the occupant, or you can control mainly a buckling in your favor. Now let's talk about finite element modeling general eigenvalue buckling basics. And whenever you start studying the fundamentals of finite element analysis on eigenvalue buckling, you see all these fancy terms like lambda or psi, then stiffness matrix, and then that is tending to 0. So this is what is the equation you see in most of this literature, which say k into E plus lambda into k into s into psi is equal to 0. Now once you go through this lot of simulation manual or open literature, you see a lot of awkward explanation for this particular equation. Now this equation is very simple to understand, and once you understand this equation, you will understand how to do this really eigenvalue buckling problem on your own. So in this equation you get a two stiffness term. The first term is a elastic stiffness matrix. The second term is the stress stiffness matrix, and that is multiplied by a eigenvalue, and this stiffness term into a eigenvector is equal to 0. So what it signifies, Once the stiffness term becomes 0, structure cannot take any more load and structure get buckle. Now try to understand how this stress stiffness matrix is built. Now you take an example, say this is a column. So you have a column which is pin or fixed at the bottom, and for the time sake you consider this load is in reverse direction. So this load is in tensile direction, not in compressive direction. So once your load is in tensile direction, this induce a positive stress stiffness, and once it's induce the positive stress stiffness, it get add to a elastic stiffness, or whatever we sometime it is called as a shape stiffness. So for example, if somebody hold your legs at the bottom and somebody pull you up, your the stress stiffness generated in your body is a positive, which will get added to your shape stiffness or the elastic stiffness of the body, which will be in your favor. Now consider another case, a column which is fixed at the bottom and the load is a compressive load. So say your legs are fixed at the bottom and somebody is trying to compress from the top. Now once you apply a compressive loading on any structure, it generates a negative stress matrix. So the stress matrix is negative. So as somebody try to push you from the top compressive loading, it is a negative stress stiffness is generated inside your body, which will take out this negative stress will reduce your overall elastic stiffness of body. So for example, if you have column and you start compressing, the stress stiffness is negative, so overall your stiffness, the elastic stiffness and the stress stiffness will reduce, and there will be one point where there will be no stiffness in a structure, and then at that point the structure get collapsed. Now how this equation, this most of these simulation solvers solve? So it's very straightforward. You take a structure, you do a finite element modeling, you apply a unit load, either a 1 Newton or 10 Newton, or you can preferably you should apply a unit load, so you can easily get a multiplication factor. You apply a load. Once you apply a load, whatever solver, for example Abaqus, it will go and calculate what is the stress matrix for that particular load. Once it is calculate the negative stress matrix for that, and then it will get overall the shape stiffness from the structural property and the material property of the structure, and then it will calculate what is the eigenvalue factor or whatever that multiplication factor is required to get this structure unstable or a buckle, and that is what particularly called as a eigenvalue. Once you multiply this eigenvalue to your unit load or whatever load you applied, that is what your critical buckling load. Whatever the eigenvectors you get, whatever displacement you get out of this equation, they are not a real displacement, but they are just a representative of a buckling shape, what buckling shape you get. So this is what is a brief about fundamentals of finite element eigenvalue buckling problem. Now very typically, for now we are talking about mainly Abaqus. Abaqus solve mainly eigenvalue problem using a two method, is called as a subspace and Langkos. You can get all the details and the advantage about these methods on open literature. And once you solve this problem, whatever the lowest eigenvalue associated with the buckling is your critical buckling load for your problem. Now let's get into more into Abaqus eigenvalue extraction method. Abaqus offers you two methods. One is a Langkos and the other is a substrate. Langkos method is very fast when we want to go with a large number of eigenvalue problem. Substrate is faster with a few eigenvalue mode. So the default method which is used in the Abaqus is a subspace method. So how this Abaqus do this buckling analysis? So Abaqus step for buckling is started with a star buckling. So once you put a star buckling, Abaqus understand it is a buckling load case, and this you have an option to select a eigenvalue solver. Default eigenvalue solver is a subspace solver. So if you just write a star buckling and you doesn't select eigenvalue solver, default solver is a subspace solver. But if you want to go for a Langkos, then you have to specify on a after the star buckling eigenvalue solver equal to Langkos. Now Abaqus, what type of load it takes for a buckling? So Abaqus take three types of load for a buckling simulation. It can take a concentrated load, which they call it as a star C load, or it can take as a distributed load, what they call as a star D load. Distributed loads means I am talking here about something like a pressure applying on a structure, or say pressure vessel subjected to a vacuum pressure. Also it have an option called a star temperature. Now star temperature very particularly here is, say suppose you have a structure which is subjected to now say 100 degrees Celsius, and then it will cool down to say a room temperature of a 20 degrees C. So like a typical thermomechanical analysis, so you apply a temperature, you apply a coefficient of thermal expansion, and you give what is the end temperature at the end of the step, and then Abaqus will calculate for this particular problem at what temperature structure will buckle. So this is a three choice different loading choice you have. Since it is a very perturbation step, or it is a linear step, you have to only use a linear elastic metal property to solve this problem. Since this problem is perturbation step, it will not take any non-linearity like a plasticity effect or strain rate effect. Those will be not considered. Now for typically for this Abaqus buckling simulation, it support any stress and displacement element, any structural element like a S4 or S3 shell element, or C3 D10M, or I like a three-dimensional continuum solid element. The only elements which you cannot use with a Abaqus solver are like a hybrid and contact element. Since it is a linear perturbation step, so the contact elements are not allowed in this procedure. Now let's try some hands-on on this buckling simulation. So let's take one simple example, very simple example which you can easily perform on yourself, and then get into understanding of buckling solver wise or theoretical wise, and we can build on from this simple example. So let's take a simple steel plate which is a 20 millimeter in width, 1 millimeter in thick, and then 400 millimeter in length. And what we are going to particularly model is really a pin condition. So for this pin condition, we'll calculate what is a critical load. So you can the units we are going to use is a Newton, millimeter, ton, Newton, MPa. So let's calculate what is the Eulerian formula gives us as a critical load. So first we'll calculate what is the area moment of inertia I, which is W into B into T cube. So 20 into 1 cube by 12, so you will get 1.667 millimeter raised to 4 as a moment of inertia. You put all the value, pi square, Young's modulus of steel, which is a 210 e raised to 03 MPa into I, divided by effective length. Since it is a pin condition, the effective length will be 1, so 400 square, and you get a critical buckling load of 21.6 Newton. Now let's try to solve this problem. So for this to solve this problem, I'm going to use a hypermesh version 11, but as a preprocessor. But if you have to try with Abaqus C, you can try with Abaqus C. So preprocessor doesn't matter. What we are mainly looking is solving in a Abaqus. I have this already modeled this plate. It is just a mesh I have modeled. So this is 20 millimeter in width, and then 400 millimeter in length. So I'm going to do a pin condition. So this end will be pin and this end will be pin, and we are going to apply some compressive load. So we'll do a setup. So I'll just first start with a metal property. So I'll say steel. You can choose any color in hypermesh, whatever you want. You select Abaqus material, you say create and edit. So it will create as a star mat, name is equal to steel. Then you click on a elastic property, you give a 2.1 e raised to 0 210 e raised to 03 as a metal property. You give a Poisson's ratio which is a 0.3 for typical steel. Then you give a thickness 1 millimeter. I just given name thickness underscore 1 millimeter. I'll say section cell, then I'll say material steel, I'll say create and edit, and then I'll say 1 millimeter thickness. And now I'll just try to connect this this particular component which I create a column with this property. So I create a property, so this update my component. I'll also choose solver as a Abaqus solver. So once you go to preference, you choose as a Abaqus solver, Abaqus 3D. Now we have seen, we are given everything connected. So this is a component which is connected to thickness 1 millimeter, which will have section shell section, steel property, and once you say updated, it's updated. Now let's create load collector name called as a pin condition. I'll say pin condition. So at the bottom I'll just put constraint. So once I go to this analysis panel, I'll go to constraint and I'll constrain all three translation, XYZ translation. That's create my pin condition. Now second thing, then I'll apply some compressive load. I'll say force name. So I'll choose a top node. So there are 4 nodes, so I'll apply in Z direction minus 1 Newton. So total I applied total minus 4 Newton load on the structure. Now really our load is only in a Z direction, so this particular load is not going to cause any X or Y displacement. So this is also almost like a pin condition. Even though we are not putting any boundary condition, this is exactly a pin condition, because we are giving load in specified load in one particular direction which is not causing any other X or Y displacement. So you done that. Also you define some output, which is output block. You create output block, create, and once you create, you say edit, then you say output is a field variable, and then you say pre-select. Pre-select means you'll get the solver will give output very specific to element, and then I'll say frequency equal to 1 or last. So we define a output, and then you say whatever node output and element output. Once you done this, so now what we have done, just to recap, we have modeled this 400 millimeter by 20 millimeter steel plate with 1 millimeter thickness. We first built a metal property called as a steel. Then we built a thickness 1 millimeter. We connected a metal property to that property parameters. Then we connected this property parameters to component. Then we created a 2 load step, 1 bottom pin condition. We apply load, which is a minus 4 Newton at the top. Now in analysis panel, you go to load step. So once you click on the load step, you give some name. So I'm giving buckling. I'm giving a name buckling. Now you select a load collector force and pin. You select a output block which we have created and say create and edit. So once you do this create and edit, 1 minute. So now let's create some load step. So you click on a load step, you give some name, you give say buckling as a name, you select load collect load and the boundary condition, you select output block and then say create, and then you click on the bottom button edit. So you see a star step, and then you see a two collector selected at the bottom, and then you see a output field. But inside the star step still we are not selected the method to solve this problem. So for example, we are not specified this is a buckling problem. So now in analysis procedure you select buckling, you selected eigensolver subspace which is a default, but in case you want to select line cause you can select a line cause also. So we have started with a subspace which is a default solver, and then you have to give how many number of eigenvalue you want to extract. I'll just put we want to extract just a 3 numbers of eigenvalue. That's it. So the input take for the eigenvalue buckling analysis is Abaqus is ready. So let me save this. So I'll just save this as a trial buckling scale pin condition. So let me save it, and let me also export this. So I'll just export this. You have to export as a INP file for Abaqus as an input file. So I just exported it. Now let's go and see what is here in a input file. So I just open in a text pad. So in text pad what you can see is you have a node which is started with star nodes, then you have elements which is named as a column. This is a 4 noded shell element S4R. R is for reduced integration, but since it is just a implicit analysis, you don't have to bother about the reduced or full integration. Then we have star section, shell section, where we are given 1 millimeter thickness. Then we have steel metal property, we are given a property. Then inside a step we have star step, buckling, eigensolver subspace, and we are saying calculate what is the first 3 eigenvalue buckling for this particular structure. We apply -4 Newton load. Bottom it is a pin condition 133, and then we have star output field variable equal to pre-select to get a output specific to this load case. Now let's try to run this. So I'll just open a Abaqus solver, and then I'm just trying to run this. So running, I'll say Abaqus J is equal to, J is nothing but a job equal to, and you just copy the name without extension. So I'm just going to write a name buckling underscore scale underscore pin, no extension, and then you say int, which is an interactive mode. So I'll just click on an interactive mode, and then from my machine it will find a solver, and then it will try to solve this problem. So I hope it will start now. So it started. Once it is started, it will go to a pre.exe. In pre.exe it will check if there is any error related to preprocessor side. Since there is no error in preprocessor side, it will go to a solver which is a standard.exe, and then it will try to solve the problem. So the problem is done now. So you see the end of job, and it will generate status file, ODB. It will have all the counter plots and the results, message file, dat file. So now let's go and see what is the results. So I'll just go for a 2 minutes to PPT, and we already know the load was a critical load based on Eulerian formula was a 21.6 Newton. So let's see what Abaqus solver has given. So here I just open a preprocessor, again HyperWorks 10 Hyperview, but you are open to do whatever preprocessor you have. Either you can do in view, you can use a Abaqus viewer also for this. So let's see. So my first eigenvalue is a rigid body mode, so I'm not interested, so I'm going to a second eigenvalue which is a 5.4022, and now we'll see some of this deformed shape, how it is deforming. So that's it. So if I have to see in proper side view, I'll just give some scale factor so you can easily watch the deformation. So this is what is a pin condition deformation, and eigenvalue what we got is a 5.4022 for our corresponding load of a -4 Newton. So if you want to really calculate what is a critical load, whatever load you have applied, multiply by this eigenvalue is your critical load. So we applied a 5 into 4 -4 Newton into 5.4022, that is our load for a critical buckling load. Now let's see what we get out of this. So I just put this in a PowerPoint so you can understand. So this is what a buckling mode shape for this 5.402 eigenvalue, which is actually similar what you see theoretically in a pin condition. The eigenvalue we got is a 5.4022. You multiply whatever the -4 Newton you applied, so you get a 21.61 Newton, which is the same what you get out of this Eulerian equation. So this is the first step, and it is a simple problem to build more on this concept to really go for a complex problem. Now let's try to tweak this problem a little bit. So now what we are going to do is we are going to change a boundary condition a little bit. So for example, if you put bottom condition as a fixed condition and then you apply compressive loading, so earlier you see it was a pin condition, now we are putting a fixed condition and a free condition, and then you try to this solve problem. So you are now the effective length is no more of 400, it will be 400 into this the factor 2, which will be 800 square. So whatever the critical load you get is a 5.4 Newton. So let's now try to, I'll just again go back to hyper mesh to make this fixed free condition. Now if you see at the bottom we have all this pin condition, so I'll first delete it. So I'll say F2 delete, I'll say loads by collector pin condition, I'll say delete, and also I'll delete the collector. I'll create a fixed condition. So I'll create a collector called a fix. I'll go to analysis, I'll go to constraint, and then I'll click all this rotation also, and I'll select the bottom nodes. I'll say create. Now it is a fixed condition. Now I'll just connect the new load case whatever we have done to a solver, and then we are again star step, buckling, subspace, 3 number of eigenvalue, -4 Newton load, fixed condition, and output block. So we are ready to run the other second problem. Now we are just building on the first problem, so I'll just give this as a fixed and then free, and then I'll just export my date here. So buckling scale, Now let's run the second problem, see what is the value we get. So I'll say Abaqus J is equal to, I just paste the file name without extension. I'll say interactive mode. So it just started. It is gone to pre.exe, where it will go and check if there is any preprocessor related error. There is no preprocessor related error. It has gone to a solver, which is a standard.exe. We are done. Now let's see how the second result looks like. It is a fixed and free condition. So you go and choose that. I'll just select this as a free as a wireframe. And so this is what actually you see how it looks. So I'll go to first one, which is in the second fixed and free condition. We don't have any rigid body mode. Out of the first mode is 1.3543, and which is a fixed and free. This is a pin. This is a fixed and free. This is the eigenvalue mode for the first eigenvalue 1.35. Now let's go and cross verify where we are standing with a Eulerian formula. So we got a 5.4 from the Eulerian formula. Now through Abaqus solver we got a 1.3543 as an eigenvalue. We apply a -4 Newton in compression direction, so our critical load is a 5.42 Newton. So it is almost closer to whatever you see through a theoretical Eulerian formula. This is the second problem you solve, and based on this we can build many more problems like this. Now let's talk about something very important about this buckling, is really how you can interpret linear buckling results, which is very important to understand how this linear buckling works. There are two types of buckling actually. If you see a real world or whatever the practical sense of can buckling, what you have seen is actually the real world. The problem is more like a non-linear problem. You start applying load, and then one particular time it goes through this bifurcation point or snap through behavior of a post buckling, and this particular non-linear behavior you start seeing a non-linear behavior because of couple of things. The real structure having a lot of this imperfection. Whenever we talk about column, it is not a perfect column. It may have some imperfection. It will be slightly tilted, or some manufacturing defect, or it is not a straight perfect column, like what you have seen in this can buckling case. It is not a really a perfect column. There will be slight imperfection in a real world problem. Also the real world problem, there is a lot of non-linearity effects. So because of this, whenever you perform a same analysis in a non-linear buckling, whatever load you get which is lower than the linear buckling problem. So whenever linear buckling problem which is based on the linear elastic modulus, so most of the time you see the bifurcation point or critical load point out of linear buckling is on higher side compared to a non-linear buckling side. So the linear buckling we have to take as a guideline to understand the critical load, where it is the number wise, and this number has to be used very cautiously, because the non-linear, the real buckling value will be lower than what you get out of this linear buckling. Also with the linear buckling, whatever mode shape this gives us the idea in which particular form or deformed shape, structure is going to buckle. So this is how you have to really interpret the linear buckling results. So that's it, guys. Now we told you the basics of buckling, we told you the fundamentals of buckling, we have done a couple of problems with you, and I guess you are ready to go on your own. Thanks a lot for watching Abaqus Acumen video. We believe in continuous improvement. You have any query or you have any question, or in case you want to have this input decks, please mail us at abaqusacumen@gmail.com. Don't forget to like our YouTube channel, and don't forget to like our Facebook page. Thank you. Bye bye.